So now we come to waves. We see beautiful water waves here. We'll be studying waves. And a wave is a kind of a disturbance that travels in a medium. Okay, so this you could say is a disturbance that's traveling forward. There are many types of waves. We are going to study mechanical waves as opposed to electromagnetic waves that you will study about in physics 2. Okay. So mechanical waves have some specific requirements. One is that there has to be a source of the disturbance, something actually producing that disturbance. Then the disturbance has to travel through some medium. So a medium is necessary, okay, which is not necessary in electromagnetic waves. And thirdly, that medium must be such that the disturbance can be propagated. So the disturbance can move forward in some way, okay? All waves carry energy and momentum. This is always true, okay? So the disturbance can carry forward some information. There are two types of waves, transverse and longitudinal. Transverse wave means something is happening in the direction perpendicular to the motion of the wave. So here is a wave being generated, and this wave is traveling out to the right, yeah, along this arrow. So the velocity, wave velocity is in this direction. The disturbance is traveling out to the right. The individual particles are traveling up and down, however. They're executing simple harmonic motion out here. So this particle here will not physically move out there with time. This is simply the medium where the disturbance will go forward, yeah? So the disturbance goes forward in the medium, the individual particle in the medium stays right here. It oscillates about this position. So its oscillation is perpendicular to the direction of motion of the wave, hence the name transverse. Okay? In longitudinal waves, this is my medium, again, like a slinky, and I'm going to give a pulse. Okay, so that's one disturbance. Over time, it has traveled out here. At some later time, it was here, and this next one is just being generated. So this wave is traveling out again to the right, and these individual particles are oscillating about their mean positions, again doing simple harmonic motion, okay, about their mean position. The particles are not traveling from here to here. They're traveling just about their mean position. But the direction of simple harmonic motion is parallel to the direction of the entire wave, hence the term longitudinal. Okay, so I hope it's clear the difference between longitudinal and transverse waves. Longitudinal waves have a compression and a sort of rarefaction, which means less density. Higher density, lower density, higher density, lower density portions. So you can see in this, for example, you see this high density area, and then there's a lower density area, and a higher density area and lower density area. So if we represent this density versus display position, then you can see that the density has peaks and troughs. This is a high density compression. This is a low density rarefaction. A high density compression, a low density rarefaction. So in longitudinal waves are also called density waves or pressure waves, because that is what is changing, okay? The actual wave does not have this sinusoidal pattern. But if you plot the density or you plot the pressure, then it does show a sinusoidal pattern. The actual wave is like this. It just has compression and rarefaction. Okay. So let's describe the wave. We've already told you what an amplitude is. The amplitude would be delta y here, the maximum displacement from equilibrium. What is delta x showing us here? It shows us the wavelength going from one peak to the next peak. Oh, here we can't see this trough, but if there was a trough here, trough to trough, or this point to the equivalent point would be somewhere there. Okay? So any two equivalent points, between them we have one wavelength. Yeah? Here's an actual water wave showing you that the wave is traveling out to the right along this green arrow, and the duck is bobbing up and down right where it is. It's not being carried forward by the wave. this is a toy duck, and it's staying right here, executing simple harmonic motion, yeah, of amplitude x. Okay, so you can see the wavelength here, the amplitude. You should be quite familiar with these things by now. The speed of the wave, speed is distance over time, yeah? So speed is the distance, one wavelength, divided by the time it takes to travel one wavelength. Yeah? This is my velocity of the wave, lambda over t. Lambda is wavelength, okay? 1 over t is nothing but frequency, so we usually write this expression in this form, which is v equals f lambda. That f is the same as 1 over t. We saw that a few slides ago. So this is a very, very fundamental equation for all waves, applies to all types of waves, electromagnetic or mechanical waves. The wave velocity is equal to frequency times lambda. You have to know this. Okay. If you look at the waves on a string, so you have a string, you produce a tension, like if you play the guitar or some stringed instrument, then people often do that. And if the tension in the string is F, okay, and mu is the linear density of the string, which means the mass per unit length. That's called linear density, okay? So the wave velocity just depends on these two factors, the tension in the string and the mass per unit length. That's fixed for a given string. So you often find people changing the tension in the string, huh? To change the frequency, because V equals F lambda. Okay. So the speed depends only upon the properties of the medium through which the disturbance travels. Here is a wave. Let's say the brown wave is the initial wave. And after some time t, this wave has moved forward, and its new position is shown by this blue wave here. So the distance that it has traveled forward is v times t, the velocity times the time, yeah?